Welcome to Foundation Mathematics, Differentiation. In this unit, we'll be looking at first and second order derivatives, equations of tangents, and classifying critical points. The objectives for this session are to explore the essential idea of the derivative as the gradient of a tangent, find the derivative of functions such as trigonometric functions, polynomials, exponentials, and logarithms, use some simple rules of differentiation to find the derivative of more complicated functions, and find the equations of tangents to curves by applying differentiation and finding and classifying critical points. The gradient of a straight line is its slope. It is calculated by dividing the vertical distance by the horizontal distance between the points. Suppose a line is joined by the points x1, y1 and x2, y2. The vertical height of the right-angled triangle generated by this line is y2 minus y1, and the horizontal length is x2 minus x1. The gradient m is therefore equal to y2 minus y1 over x2 minus x1, as shown. Let's now take a look at an example. Find the gradient of the line which joins the points minus 3, 8 and 3, 6. We can draw a sketch of this just to give us an idea of what is happening if we need some clarity. So therefore, m equals y2 minus y1 over x2 minus x1, which equals minus 2 over 6. And this is of course equal to minus 1/3. So the gradient m equals minus 1/3. A curve has a constantly changing gradient or slope. It is possible to find the gradient of the curve at a point by finding the tangent at that point. The straight line that just touches the curve at a point is the tangent at that point. So we can say that the gradient of a curve at a point is the gradient of the tangent at that point. Let's take a look at an example to illustrate this. For the curve y equals x cubed minus 6x squared plus 11x minus 6, we will find the gradient of the curve by using a sketch. So here's a sketch of the curve. And here's the line at a particular point on the curve. The tangent to this curve has gradient 2 at 3, 0. Notice that it just touches the curve at this point. Let's take a look at another example. We will find the gradient for the curve y equals a half x squared at the point 0.5, 0.125. So here's the curve, and here's the line or the tangent just touching the curve at the point 0.5, 0.125. Let's solve this. So we first find the tangents of lines which don't just touch the curve, but move towards the line which does. So we're going to find the gradient of the line which joins 0.5, function of 0.5, to 1.5, function of 1.5. So here's 0.5 highlighted on the graph, and here's function of 0.5. And here's a line which doesn't just touch the curve, but is not too far off from touching the curve. It's 1.5, function of 1.5. Let's find the gradient. It's this difference, highlighted with the blue arrow, which is equal to 1, because it's function of 1.5 minus function of 0.5, divided by this distance, which also happens to be 1, because it's 1.5 minus 0.5. So the gradient is equal to 1 divided by 1, which equals 1. Now, of course, this isn't the gradient that we're looking for. Let's now find the gradient of a line which joins 0.5 function of 0.5 to 1.1 function of 1.1. Notice that this is now getting closer to our desired gradient. We've indicated the points on the curve where the line and the curve intersect. So at 0.5 function of 0.5 and 1.1 function of 1.1. So the gradient is going to be change in y, as highlighted with the blue arrow, which is equal to 0.48, divided by change in x, which is 1.1 minus 0.5. So the gradient equals 0.48 divided by 0.6, which is equal to 0.8. Now let's find the gradient of another line. As shown, again, as you can see, this is getting closer and closer to our desired tangent. The gradient of this line is change in y, as highlighted, over change in x. So the gradient equals 0.28 divided by 0.4, which is equal to 0.7. Now let's find the gradient of our actual line. This time we're going to pick a point on the tangent at 0.5, comma, f of 0.5. So gradient of y equals a half x squared at this point is equal to change in y of this tangent divided by change in x, which equals 0.5. Now you may be wondering why we didn't calculate this in the first place. Notice that this tangent is actually an approximation. All the other tangents that we've calculated, well, they're not actually tangents, but all the other lines' gradients that we've calculated are exact. They aren't tangents to the curve, but they are approaching the point that we are interested in. Let's see if there's a link between their gradients and the gradient which we have estimated from the graph. So remember the first gradient, which was the furthest away from this line, had a gradient of 1. The second gradient, which was now getting closer, was 0.8. And the third gradient was 0.7. So here's a summary. 1, 0.8, 0.7, 0.5. The gradients all seem to be approaching 0.5. Bearing this example in mind, let's see if we can get something more precise regarding the tangent at a point on the curve. So consider first a continuous function f of x. We also consider some point c on the x-axis. This is sent to f of c on the y-axis. Now consider the value c plus h on the x-axis. This is sent to the value f of c plus h on the y-axis. Notice that the red dotted line denotes the gradient at the point C. It is clearly not going to be easy to find this gradient exactly from the graph. One way to find it is to consider the gradient of the line joining f of c to f of c plus h. And looking at the diagram, as b moves closer to a, the gradient of AB approaches the gradient of the tangent to the curve at A. The gradient of the line joining f of c to f of c plus h is change in y, as shown by the blue line indicated by an arrow, divided by change in x, which is equal to h. So as h gets closer and closer to 0, the gradient of the thick red line approaches the gradient of the line at C, as you can see. So we can write this as the derivative of f at C is the limit as h tends to 0 of f of c plus h minus f of c over h. So if we define this formally, the gradient function or derivative of the curve y equals f of x is written f dash of x or dy dx and is given by f dash of x equals lim as h tends to 0 f of x plus h minus f of x all over h. The gradient can be used to find the gradient for any value of x. Let's take a look at this notation. Lim h tends to 0 means the limit as h tends to 0. The expression cannot be evaluated when h equals 0, but as h becomes smaller, the expression approaches a fixed or limiting value. Let's now take a look at an example. The point A with coordinates 2, 8 lies on the curve with equation y equals x cubed. Find the gradient at the point A. So let's solve this. Now dy dx equals lim as h tends to 0 of f of 2 plus h minus f of 2 all over h. We've simply substituted in our particular values into this equation. And this in turn equals 2 plus h all cubed, because we're looking at y equals x cubed, minus 2 cubed all over h. And so expanding the first set of brackets gives the expression shown. And then tidying up gives us this expression. And now we can factorize the numerator as shown, and cancel to give us lim h tending to 0, 12 plus 9h plus h squared. And this is of course going to equal 12 if we let h tend to 0. Now let's take a look at another example. Working directly from the definition, find the gradient function of f of x at a for a not equal to 0. Here, f of x is equal to 1 over x squared. So let's solve this. Applying our formula, here, gives us 1 over a plus h all squared minus 1 over a squared all over h. And then tidying up gives us this expression. Then factorising the numerator and cancelling the h's in the numerator and denominator, gives us this expression here. And if we let h tend to 0, we obtain minus 2 over a cubed. We are now going to take a look at differentiating x to the power n. The process of finding the derivative of any number is called differentiation for all real values of n and for a constant a. We have that if f of x equals x to the power n, then f dash of x equals n times x to the power n minus 1. Or, using slightly different notation, if y equals x to the power n, then dy dx equals n times x to the power n minus 1. And similarly, if f of x equals a times x to the power n, then f dash of x equals a times n times x to the power n minus 1. And here's the equivalent notation if y equals a times x to the power n. We aren't going to prove this in this session. However, if you're enthusiastic, you are more than welcome to give it a try. We will be looking, however, at this example. Pause the video and have a go. Press play when you're ready to view the solutions. We are going to begin by solving part A first. Find the derivative of f of x equals x to the power 7. Now, if f of x equals x to the power n, then we know from our formulae that f dash of x equals n times x to the power n minus 1. So here we simply substitute in the values for our particular example. We have n equals 7, as you can see. And if we plug that in, we obtain 7 times x to the power 7 minus 1, which equals 7x to the power 6. And now for part B. Again, we use the same formula because it's x to the power something. And then we simply plug in the value for n equals 1/3. Now we're required to find the derivative of x to the power minus 5. Again, the rule doesn't change. We simply apply the same formula because we're doing x to the power n. So the derivative, of course, is again n times x to the power n minus 1. And plugging in n equals -5 gives us -5x to the -6. Let's now have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. We begin by finding the derivative of y equals 8x to the power 4. This time we're going to use this formula because we have a constant at the front. And so plugging in all the values, we have a equals 8 and n equals 4 to give us dy dx equals 8 times 4 times x to the power 4 minus 1, which tidies up to give 32 x cubed. And now for example B, find the derivative of y equals -5 times x to the power 1 over 5. Again, we're going to use the same formula because we have a constant at the front as well as a power. So if we plug in a equals -5 and n equals 1/5, we obtain dy dx equals -5 times a fifth times x to the power a fifth minus 1, which tidies up to give -1 times x to the power -4/5. And now for example C, find the derivative of y equals 3x to the power -3. We're going to use the same formula because we have a constant a equals 3 and n equals -3, which we plug in to give 3 times -3 times x to the power -3 minus 1, which tidies up to -9 times x to the power -4. Let's now see what happens when we differentiate multiple terms. So if y equals f of x plus or minus g of x, then we have that dy dx equals f dash of x plus or minus g dash of x, where f dash of x and g dash of x are the differentiated expressions of f of x and g of x respectively. Let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve part A. If we have y equals 2x cubed plus 9x, let's differentiate term by term. So we have dy dx equals 2 times 3 times x to the power 3 minus 1 plus 9. How did we obtain this? We've simply plugged in the values for a and n for this particular term into our formula. So we obtained for 2x cubed a equals 2 and n equals 3, and we plugged that into dy dx equals an times x to the n minus 1. Similarly for 9x, here we have that a equals 9 and n equals 1, and we've plugged that in to find dy dx for 9x. And then tidying up gives us dy dx equals 6x squared plus 9. Now let's solve part B. So if y equals this expression here, then dy dx equals this expression. Let's break this down term by term. So for the term x to the power 4, we have that a equals 1 and n equals 4. And this gives us the resulting dy dx for this term. For the term x cubed, we have a equals 1 and n equals 3. And hence dy dx equals 3 times x to the 3 minus 1. And finally, for the term minus 2x to the power a half, a is equal to minus 2 and n is equal to a half. So we have this slightly complicated expression highlighted in red for dy dx for this term. We can therefore tidy up to obtain dy dx equals 4x cubed plus 3x squared minus x to the power minus a half. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve part A. We are required to differentiate this expression for y. Now if y equals 2 over 5 times the cube root of x, then clearly we need to rearrange or re-express this in a form that we can work with and then differentiate. So let's rewrite this in a slightly more convenient form. We can express this as y equals 2 over 5 times x to the third. However, this is still not quite in a format that we can work with to find differentials. So here's where 2 over 5 came from, and here's where x to the 1/3 came from. So this is 2/5 times x to the power minus 1/3. Now this is in a form a constant times x to the power a constant. So we can work with this and we can differentiate. When we differentiate, we plug in a equals 2/5 and n equals minus 1/3 to give us the expression for dy dx as shown on your screen. Here's where the 2/5 came from. This is a. And here's where the n came from. Notice that we've plugged this in to dy dx as shown from the formula. And then tidying up gives us minus 2 over 15 multiplied by x to the minus 1 and a third. Now let's solve part B. We are required to differentiate y equals x to the power 4 times 2x minus 3. Again, this is not quite in a format that we can work with. So we need to rewrite this so that we can work with it and differentiate. So if y equals x to the 4 times 2x minus 3, then multiplying out gives us that y equals 2x to the power 5 minus 3x to the power 4. Here we have 2x to the power 5, and here we have minus 3x to the power 4. Now we can differentiate term by term. So for the term 2x to the power 5, we have a equals 2 and n equals 5. And again, simply plugging into the formula for dy dx gives us the expression shown. And for the second term, minus 3x to the power 4, here we have a equals minus 3 and n equals 4, giving us the expression for dy dx. And so if we tidy up, we obtain 10x to the power 4 minus 12x cubed. Here's a summary of the key points. We're going to look at an example in order to understand some of these points in greater depth. Find the equation of the tangent to the curve y equals 5x cubed plus 2x squared minus 3x minus 1 at the point 1, 3. Let's solve this. So we have y equals this cubic, and therefore the gradient of the tangent is dy dx equals 15x squared plus 4x minus 3. We've used, of course, the formula dy dx equals an times x to the n minus 1 for each term. And therefore, when x equals 1, the gradient is 15 times 1 squared plus 4 times 1 minus 3, which is equal to 16. So the equation of the tangent at 1, 3, substituting in this equation for the tangent at A, is y minus 3 equals 16 times x minus 1. This is where we get 16 from, and this is where we get 1 from, and this is where we get 3 from. And therefore rearranging gives us that y equals 16x minus 13. The derivative of a function can help determine whether it is increasing or decreasing. The function f of x is increasing on interval ab if f dash of x is greater than or equal to 0 for all values of x such that a is less than x is less than b. And it is decreasing on interval ab if f dash of x is less than or equal to 0 for all values of x such that a is less than x is less than b. Let's take a look at an example. The function f of x equals x to the 5 plus x looks something like this. Notice that it is an increasing function, and it is increasing for all real values of x. Let's take a look at another example. In this example, we look at the function f of x equals x to the 4 minus 2x squared plus 1. This looks something like the graph you can see on your screen here at the bottom. Notice that the function decreases to the point x equals minus 1. Then it increases to the point x equals 0. So it is increasing on the interval minus 1, 0. Then it decreases to x equals 1. So it is decreasing on 0, 1. And then it increases again after x equals 1. Let's now take a look at another example. Show that the function f of x equals 2x cubed plus 5x minus 7 is increasing for all real values of x. So let's solve this. Now f dash of x equals 6x squared plus 5. If you've forgotten how to differentiate, note the rules for differentiation towards the bottom of your screen. 2x cubed differentiated becomes 6x squared, applying this rule, and 5x differentiated becomes 5. And of course the minus 7 is going to be 0 when differentiated because it's a constant. Now, since x squared is greater than or equal to 0 for all real values of x, we have that 6x squared plus 5 is greater than 0 for all real values of x also. And therefore, f of x is increasing for all real values of x. And this comes from this statement shown here. To find the rate of change of the gradient function, you can differentiate again. Differentiating a function y equals f of x twice gives the second order derivative f double dash of x, or d2y dx squared. Let's take a look at an example. If y equals 3x to the power 5, we can differentiate by using this formula to obtain dy dx equals 15x to the power 4. We can differentiate this again by using this formula to obtain d2y dx squared equals 60x cubed. dy dx is the gradient function which describes the rate of change of x. And the second derivative, d2y dx squared, is the rate of change of the gradient function. Let's now take a look at some notation. For a function y equals f of x, the first order derivative is given by f dash of x, or dy dx. And the second order derivative is given by f double dash of x, or d2y dx squared. Now let's try another example. Given that y equals 7 root x plus 6 over root x, find f dash of x and f double dash of x. So let's solve this. We're rewriting y in a form that will allow us to calculate dy dx, or f dash of x. So 7 root x becomes 7x to the power a half, and 6 over root x becomes 6x to the power minus a half. And therefore, differentiating the first term, applying the highlighted formula, gives us 7 times a half times x to the power a half minus 1. And to the second term, we obtain 6 times minus a half times x to the minus a half minus 1. Of course, we've simply applied the highlighted formula. And tidying up gives us 7 over 2 x to the minus a half minus 3x to the minus 3 over 2. And differentiating again, using the formula for f double dash of x, and applying it to the first term, gives us 7 times a half minus 1 times x to the power half minus 2. And applying it to the second term gives us 7 times minus a half times minus a half minus 1 times x to the power minus a half minus 2. And tidying up gives us minus 7 over 4x to the minus 3 over 2 plus 9 over 2 times x to the minus 5 over 2. And so we've found f dash of x and f double dash of x. A stationary point on a curve is a point where the curve has gradient 0. A stationary point can be a local maximum, a local minimum, or a point of inflection. Note that we are showing parts of the curves here only. The nature of the stationary point can be determined by examining the gradient of the curve on both sides. So for curve y equals f of x, when f dash of x equals 0, we have a stationary point. If we look just before the x, or just before the turning point, on the maximum turning point, we can see that the gradient of f dash of x minus h is greater than 0. So just before the maximum, the gradient is greater than 0. At f of x, the gradient is 0. And after x, the gradient is less than 0. So f dash of x plus h is less than 0. Similarly, we can examine the minimum stationary point. Here, at x minus h, f dash of x minus h is less than 0. At x, f dash of x is equal to 0. And after x, at x plus h, f dash of x plus h is greater than 0. Again, for the point of inflection, let's have a look what happens just before the stationary point. So at x minus h, f dash of x minus h is greater than 0. At x, f dash of x is equal to 0. And after x, f dash of x plus h is greater than 0. And here's a summary. For a local maximum, f dash of x minus h is positive, f dash is 0, and f dash of x plus h is negative. For a local minimum, f dash of x minus h is negative, f dash of x is 0, and f dash of x plus h is positive. And for the point of inflection that you can see, f dash of x minus h is positive, f dash of x is 0, and f dash of x plus h is also positive. However, there is another type of point of inflection, and that is this one that you can see here. And this point of inflection has f dash of x minus h negative, f dash of x equal to 0, and f dash of x plus h also negative. Why do we call these points local maximum and local minimum? In the above, we have only shown parts of the functions. What happens beyond the endpoints? So at these points indicated here, if the pattern remains the same, then the points are maximum and minimum. However, if it changes, then the points are local maximum and local minimum. Here are examples of local maximum and minimum. Point A is a local maximum, as the function can take larger values. At A, this is the largest value in its immediate vicinity. And similarly, for point B is a local minimum, as the function can take smaller values. At B, this is the smallest value in its immediate vicinity. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. Before we look at this example, let's examine the steps for finding the stationary points. First, find dy dx and put it equal to 0. Next, solve for x, and then substitute x in the original equation to find y. Now let's explore the steps to determine the type of stationary point that we have. We need to first find the gradients of values slightly greater and slightly less than this x, and then deduce the shape of the curve. Let's solve part A first. We are required to find the coordinates of the stationary points on the curve with the equation y equals x cubed plus 2x squared. So let's first find dy dx and put it equal to 0. Now y equals x cubed plus 2x squared. Recall the rules for differentiation. Hence, dy dx is equal to 3x squared, applying dy dx equals an times x to the power n minus 1, plus 4x, again applying the same formula. Let dy dx equal 0, and then we have 3x squared plus 4x equals 0. So let's now solve for x. Factorising gives us that x times 3x plus 4 equals 0. And therefore the stationary points are at x equals 0 and x equals minus 4 over 3. From here and from here. Now we substitute x in the original equation to find y. When x equals 0, we have that y equals 0 also. And when x equals minus 4 over 3, we simply substitute this value into the equation for y, and simplify to obtain y equals 1 and 5 over 27. So the stationary points are at 0, 0 and minus 1 and a third, comma, 1 and 5/27. Now let's solve part B. By considering points on both sides of each stationary point, we are required to determine whether it is a local maximum, a local minimum, or a point of inflection. For point 0, 0, we are required to consider the gradient on either side of x equals 0. The points which we are going to consider on either side of x equals 0 are x equals minus 0.1 and x equals 0.1. We know that at x equals 0, we have a gradient of 0, and therefore this is a stationary point. So the shape of the curve is simply flat, as shown. For x equals minus 0.1, we're going to substitute this value in the equation for dy dx, as shown, to give us a negative value. So at x equals minus 0.1, we have a negative gradient, and therefore the shape of the curve is as shown in the table. Let's do likewise for x equals 0.1. Plug this value in to dy dx. This time we obtain a positive value. Therefore, at x equals 0.1, the gradient is positive and the shape of the curve is as shown. And therefore, we have that 0, 0 is a local minimum. Now let's look at the other stationary point. We're going to find the gradient on both sides of x equals minus 1.3. We are in particular going to look at the points x equals minus 1.4 and x equals minus 1.2. Of course, we know that the gradient at x equals minus 1.33 recurring is equal to 0. So the shape of the curve is actually flat at that point. At x equals minus 1.4, again, we simply plug into the equation for dy dx as shown, and this gives us a positive value. So our curve is sloping as shown in the table. And now let's plug in the value for x equals minus 1.2 into our equation for dy dx, as shown. And this gives us a negative value. So our curve is sloping the other way. And therefore, this stationary point is a local maximum. Sometimes you can use the second order derivative f double dash of x or d2y dx squared to find the nature of the stationary point also. How do we do this? The second derivative f double dash of x gives the rate of change of the gradient function. At a stationary point x equals a, when f double dash of x is greater than 0, then the gradient is increasing from a negative to a positive value. So the stationary point is minimum. So at a stationary point x equals a, if f double dash of a is greater than 0, we have a local minimum. Now when f double dash of x is less than 0, the gradient is decreasing from a positive to a negative value. So the stationary point is a maximum. And therefore, if f double dash of a is less than 0, then we have a local maximum. Now, if f double dash of a equals 0, then we actually can't say anything, and we need to use the other method. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve part A first. We are required to find the coordinates of the stationary points on the curve with equation y equals 2x cubed minus 15x squared plus 36x plus 2. Remind yourself of the rules for differentiation shown at the bottom of your screen. And let's solve. So applying the rule for differentiation gives us dy dx equals 6x squared minus 30x plus 36. And factorising, gives us dy dx equals 6 times x minus 2 times x minus 3. If we put dy dx equal to 0, we have that either x equals 2 or x equals 3. Now let's substitute x equals 2 in the equation for y to obtain the y value. So plugging in x equals 2 in the equation for y gives us y equals 30. Now when x equals 3, we plug in the value x equals 3 into the equation for y, as shown, to give us y equals 29. So when x equals 2, y equals 30, and when x equals 3, y equals 29. So the stationary points are 2, 30 and 3, 29. Now let's solve part B. We are required to find d2y dx squared and use it to determine the nature of the stationary points. Recall the steps to determine the type of stationary point. Remember, if d2y dx squared is greater than 0, we have a local minimum. If it's less than 0, we have a local maximum. And if it's equal to 0, we can't say, and we need to use another method. So let's solve this. So let's summarize the information that we already have. We have the equation for y. We also have from part A the stationary points, and we can remind ourselves of the rules for differentiation at the bottom of the screen. So we can now find d2y dx squared. Applying the formula a second time, we obtain d2y dx squared equals 12x minus 30. Remember that differentiating 6x squared gives us 12x, and differentiating minus 30x plus 36 gives us minus 30. When x equals 2, which is one of the stationary points, d2y dx squared equals minus 6. This is less than 0, and therefore 2, 30 is a local maximum. Now when x equals 3, d2y dx squared equals 6. Clearly this is positive. And therefore 329 is a local minimum. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's remind ourselves of the rules for differentiation first. So let's take a look at part A. The curve with equation y equals 6 over x plus 8x cubed has stationary points at x equals plus and minus a. Find the value of a. So let's solve this. We're going to put y equal to 6x to the minus 1 plus 8x cubed, because this will allow us to differentiate more easily. So differentiating gives us dy dx equals minus 6x to the minus 2 plus 24x squared. Now let's put dy dx equal to 0 to find the stationary points. So of course this implies minus 6x to the minus 2 plus 24x squared equals 0. And so multiplying out by x squared gives us minus 6 plus 24x to the 4 equals 0. And solving for x gives us x to the 4 equals 1 over 4. And therefore x equals plus or minus 1 over root 2. Hence we have that a equals 1 over root 2. Now let's sketch the graph of y equals 6 over x plus 8x cubed. So here is the key information from part A. When x equals 1 over root 2, substituting this into the equation for y gives us that y equals 6 root 2 plus 8 over root 2 cubed. And tidying up gives us that y equals 8 root 2 at this point. Now let's find d2y dx squared in order to find the nature of this turning point. d2y dx squared is equal to 12x to the minus 3 plus 48x. And so plugging in x equals 1 over root 2 into the equation for d2y dx squared gives us that d2y dx squared is greater than 0 at this point. And therefore, we have a local minimum. Now let's look at the other stationary point, x equals minus 1 over root 2, and plug that in to the equation for y. Tidying up gives us y equals minus 8 root 2. And so we have a stationary point at x equals minus 1 over root 2, y equals minus 8 root 2. Now let's differentiate again in order to find the nature of this turning point. So differentiating again gives us d2y dx squared equals 12x to the minus 3 plus 48x. And so when x equals minus 1 over root 2, d2y dx squared is less than 0. And of course this implies that our stationary point is a local maximum. Here's the key information that we have from part B. We can use that to plot our graph. Remember that one of our stationary points was 1 over root 2, h root 2, and that was a local minimum, which is here. The other stationary point was here. It was a local maximum. We also have an asymptote at x equals 0, because y equals 6 over x, so clearly we're never going to actually get a value for x equals 0. We also can look at what happens when x tends to 0 from the positive side. When that's happening, clearly we're getting larger and larger and larger values of y, and therefore y tends to infinity as x approaches 0 from above. And when x approaches 0 from below, y tends to minus infinity. So here's our graph. We're now going to take a look at modelling with differentiation. Let's begin by looking at the rate of change. The rate of change of y with respect to x is represented by dy dx, or small change in y over small change in x. Let's take a look at an example. The surface area a centimeters squared of an expanding sphere of radius r centimeters is a equals 4 pi r squared. Find the rate of change of the area with respect to the radius. Let's try solving this. Now the surface area a equals 4 pi r squared. As given in the question. Therefore, if we differentiate this with respect to r, we obtain dA dr equals 8 pi r. And this is the rate of change of the area with respect to the radius. Let's take a look at another example. Suppose that you have an expanding cylinder with radius r and height 2r. Find the rate of change of the volume V with respect to r at the instant when r is equal to 3. Let's try solving this. The volume of the cylinder is V equals pi r squared, in other words the area of the base, multiplied by the height. So here's the height, 2r, and if we tidy up, we obtain 2 pi r cubed. So therefore we have that the volume is equal to 2 pi r cubed. And therefore if we differentiate, we obtain 6 pi r squared. Now when r is equal to 3, dv dr, which is equal to 6 pi r squared, becomes 6 pi 3 squared, because we're substituting r equals 3 into the formula. And this gives us 54 pi. We can also prove the more general results. If y equals sine kx, then dy dx equals k cos kx. And if y equals cos kx, then dy dx equals minus k sine kx. Pause the video and have a go at this example. Press play when you're ready to view the solutions. So let's take a look at part A first. We are required to find dy dx given that y equals sine 3x. So let's solve this. We have y equals sine 3x. And so, using k equals 3 in the standard result for sine kx, we have that dy dx equals 3 cos 3x. And now for part B. We are required to find dy dx given that y equals cos 8x. So let's solve this. We have y equals cos 8x, and so we can use k equals 8 in the standard result for cos kx to give us dy dx equals minus 8 sine 8x. And now for part C. We are required to find dy dx given that y equals 2 sine x plus 4 cos 5x. So let's solve this. We're going to solve this term by term. So for the first term, differentiating sine x gives us cos x, and therefore dy dx equals 2 cos x plus the differential of 4 cos 5x. And we work that out by applying k equals 5 to the formula for the differential of cos kx, as shown here, to give us the term 4 times minus 5 sine 5x as shown. And so tidying up gives us that dy dx equals 2 cos x minus 20 sine 5x. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. We are required to find the stationary points of the curve with equation y equals a half x minus sine 2x in the interval x greater than or equal to minus pi by 2 and less than or equal to pi by 2. So let's solve this. If we differentiate the expression for y, we have that dy dx equals a half, since differentiating a half x becomes a half, minus 2 cos 2x, since differentiating sine 2x gives us 2 cos 2x, with k equal to 2. At the stationary points, dy dx is equal to 0. And therefore, if we solve for x, the expression a half minus 2 cos 2x equals 0, we obtain cos 2x equals 1 over 4. As we can see from the cast diagram, cos is positive in the first and the fourth quadrants. So 2x equals 1.318 from our calculator in the first quadrant, as shown here. And so in the fourth quadrant, 2x equals minus 1.318. Therefore, x equals 0.659 or minus 0.659 in the interval x greater than or equal to minus pi by 2 and less than or equal to pi by 2. Now when x equals 0.659, we have that y is equal to minus 0.639. We've simply substituted the value of x into the formula for y to obtain this. When x equals minus 0.659, we have that y is equal to 0.639. And therefore, the stationary points of y equals a half x minus sine 2x in the interval x greater than or equal to minus pi by 2 and less than or equal to pi by 2 are 0.659, minus 0.639 and minus 0.659, 0.639. Let's begin by reminding ourselves of derivatives involving exponentials and logarithms. Remember that if y equals e to the power kx, then dy dx equals k times e to the power kx. And if y equals ln of x, then dy dx equals 1 over x. Now for any constant k, ln kx equals ln k plus ln x. Now since ln k is a constant, we have that the derivative of ln kx is also 1 over x. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. We are required to find dy dx given that y equals e to the power 5x. So let's solve this. Now y equals e to the power 5x implies dy dx equals 5e to the power 5x. Here, of course, k is equal to 5. Now let's take a look at part B. We are required to find dy dx given that y equals ln 3x. So let's solve this. Remember that ln kx equals ln k plus ln x. So letting k equals 3x gives us y equals ln 3 plus ln x. And so if we differentiate this, we obtain dy dx equals 1 over x, since ln 3 is a constant. Now let's consider part C. We are required to find dy dx given that y equals 5 minus 4e to the power 4x all over 2e to the power 9x. So let's solve this. We can rewrite the expression for y as 5 over 2 times e to the power minus 9x minus 4 over 2 times e to the power 4x minus 9x. Which is equal to 5 over 2 times e to the power minus 9x minus 2 times e to the power minus 5x. And so we have our expression for y. And so if we differentiate this, we obtain for the first term 5 over 2 times minus 9 e to the power minus 9x, as shown here. And for the second term, we obtain minus 2 times minus 5 times e to the power minus 5x. We've simply replaced k by minus 5 in this expression. And so we have this expression for dy dx. So now let's tidy up. And so we have minus 45 over 2 times e to the power minus 9x plus 10 times e to the power minus 5x. This brings us to the end of this session. To understand its contents, you should be able to understand the essential idea of the derivative as the gradient of a tangent, find the derivative of functions such as trigonometric functions, polynomials, exponentials, and logarithms, use some simple rules of differentiation to find the derivative of more complicated functions, and find the equations of tangents to curves by applying differentiation and finding and classifying critical points. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.